Okay. Welcome everyone. So today we have Dr. McCartney from UC San Diego visiting us. He's a professor at UC San Diego in the Department of Structural Engineering. So I think it's the only department in the country that is structural engineering department, not the civil engineering. And he's also the department chair in that department. And he has also a number of awards very recently, as well as in the past, the NSF Career and other. And his area is in geotechnical engineering. And he's also the editor of the Journal of Geotechnical and Geoenvironmental Engineering and Computers and Geoscience. So, geotechnics, I'm sorry. So please join me in welcoming Dr. McCartney.
Thank you. So it's very nice to see you all. I always get some comments. Well, you're a geotechnical engineer in a structural engineering department. But we say the structural engineering is a holistic umbrella that encompasses anything that transfers stresses from one point to another. So geotechnical, in that sense, fits into that definition. So I'm very happy to be here today. I met many faculty today, had some great meetings. So my first time here at University of Houston. Hopefully come back again in the future. So my presentation today is going to focus on energy piles. So these are deep foundations that we use to support buildings. They were also trying to get something else out of them. In this case, thermal energy. And I'm going to talk to you a little bit today about how our process of extracting heat from the ground or injecting heat from the ground through your deep foundation could lead to changes in stress and strain. And if in the case that the soil around the foundation is inert, you're still going to have some resistance to the thermal expansion and contraction that are going to lead to some additional thermal stresses imposed on top of the stresses associated with the building. And then in other cases, in some challenging soil deposits, the heat could actually change the behavior of the soil. In unsaturated soils, the heat could drive water away from the pile, and that could increase your effective stress at the pile soil interface and potentially increase your capacity. And in saturated clays, you could actually cause the soil to contract and consolidate due to the increase in temperature. So I'll talk about all of those different concepts. It's working earlier. It's because no, it's okay. I think I needed to just click on the screen. Okay, so here's the overview. I'll tell you a little bit about why we want to change our deep foundations to energy piles. Then I'll talk about the thermal and thermomechanical response of energy piles in general, just the concepts so you can understand about it. And then the rest of the presentation, I'm going to focus on the thermomechanical analyses. I'll tell you a little bit about finite element analyses that you could perform to look at the thermal stresses and strains. And one of the reasons that this is not the most popular technique used in practice right now, because you need to get a lot of information to perform those more sophisticated analyses. And then I'll talk about the thermal load transfer analysis. And load transfer analysis had a lot of development from here at the University of Houston from Professor Mike O'Neill. So I'll actually show some plots that were from the tests here at this university. Then I'll go through 3 case histories. The first case history is for a building at the U.S. Air Force Academy. So my research in this area started when I was at University of Colorado in Boulder. So Air Force Academy is in Colorado Springs. So that's the reason that we built that particular structure. And in that case, I wanted that to be a structure that is having inert soil around the energy pile. So here, the stresses and strains should be just due to the restraint provided by the foundation. And then I want to show 2 more special challenging cases. We can't necessarily do these in the field because you can't always find the particular settings. So I'm going to look at centrifuge modeling as a tool to look at energy piles under realistic stress states for the unsaturated conditions and then the soft play conditions, and then close it out with some final comments. So why are we interested in developing energy piles? First, everybody knows this, it's in the news a lot. We use a lot of energy, and in particular, our buildings consume a large fraction of the energy that we generate. The ways that we generate electricity to energy for these buildings is usually from carbon sources, and that could potentially be polluting for the environment. So if we're able to reduce the amount of energy consumption from our buildings, we can reduce carbon emissions and have a more sustainable approach. If you look at all the different ways that buildings use energy, heating, cooling, and water heat are some of the major sources. Lights also fall into that category, although I think since this chart was developed in 2008, we've developed a lot of new LEDs, so that's probably reduced, and now heating and cooling is probably the major source of energy. So the solution to this, there's a broad set of research areas inside of geotechnical engineering that my colleagues and I have developed into the new field of energy geotechnics. This is kind of a new name that's encompassing everything in geotechnical engineering that involves energy. So I highlighted energy piles here, which is the focus of this presentation. So that's in the category of low temperature heat exchange. We're not generating electricity, we're just moving it from one place to another. In this case, we're going to be moving it from the ground to our building or from the building to the ground. But there's other areas in energy geotechnics that could be relevant to addressing this. Energy storage, either through heat or through hydropower. We could also generate electricity by going down to the deep rock to get enhanced geothermal systems, which piggybacks on petroleum engineering a lot. And then also methane hydrates, where you go offshore and get these special sediments that have methane inside of them. And then also there's a lot of infrastructure that we need to build in geotechnical engineering to make sure that these energy systems are going to be able to integrate into our grid. And finally, nuclear waste is another area that we need to manage the waste byproducts in the long term. So energy geotechnics is a very exciting new field. Hopefully, I'll show you a little bit about why energy piles are a good strategy as part of that field. I also wanted to kind of just show a couple motivating factors here. I think that there are some key questions from society. So how can we get thermal energy? Historically, the way that we've gotten thermal energy is burning wood, burning oil, burning natural gas. And in some cases, natural gas is going to be the cheapest way to heat things. But how can we make sure that the way that we're getting that thermal energy is sustainable? And then once you have the thermal energy, how do you store it? The ground is actually a very nice thermal storage medium. In some cases, we have too much heat. So in Houston, you can imagine in summer months, it gets very hot. We want to move that heat and put it somewhere else so we can cool our buildings. Right now, air source heat exchangers basically dump all the additional heat out to the atmosphere. So by cooling your building, you're heating up your outside area. If you can put that into the ground and maybe even use that heat for something positive, I think that could be a future potential. And if we do get this thermal energy, how can we make sure that we're using it efficiently? So geostructural, I put that to be more all-encompassing because actually structural engineers are sometimes the responsible people to build deep foundations. The subsurface is a good insulator. It's a good heat storage medium. The subsurface naturally stores the heat from the sun. So the sun is heating the ground, it's transferring into the ground, and then because of the low thermal conductivity, it's not releasing it out to the atmosphere right away. And then geostructural engineers are installing things in the ground. So we can use anything that we put into the ground as a way to transfer the heat in or out. And that's where the concept of energy piles come from. So I try to categorize thermal energy as 3 different techniques. One is a natural resource, which is going to be the main focus of this presentation, where we're taking the heat to heat our building or using it as a heat sink. Second, it could be a waste or a byproduct. We generate a lot of heat through industrial processes. We need to get rid of this. there's been some studies in UK that says that if everybody adopts geothermal systems, you could be having some competition over the heating of the ground. So you don't want to heat your neighbor's area too hot, to too high of a temperature. And finally, I think that the future of this area is using thermal energy as a tool. As I mentioned, we can use the heat to dry soils. We can use the heat to consolidate soils. Maybe even in the future, use heat to help remediate contaminated soils and modify processes in things like landfills or provide de-icing. So I think there's a lot of potential there. So now I'm going to focus on ground source heat exchangers in general. So I always have to mention that ground source heat pumps do not generate electricity. They just are a tool to move heat from one place to another. It's the same technology that is used to move heat out of your refrigerator or your freezer to keep it cold. You're using a refrigerant loop that is expanding and contracting a refrigerant material, converting it from a gas to a liquid to help exchange heat and move it from one place to another. So that's through this heat pump cycle that you can see up here. And we're just going to connect that heat pump cycle to a loop of pipe, a closed loop pipe that is inside of our deep foundation. And we're going to circulate water or an antifreeze solution in the case that you're having low temperatures to exchange heat via convection in the pipe to conduction into the pile and then conduction into the surrounding soil. And the people say, well, ground source heat pumps are only good for North Dakota because it's cold there. Actually, it works anywhere. Your refrigerator works here and it works in another place. The efficiency is going to be different depending on where you go. And we can use some design tools to make sure that it works wherever you want it to be. So just a couple comments about this refrigerant loop. So if you want to heat your building, you're going to put cold fluid into your foundation. That cold fluid is going to warm up and bring warmer fluid back to your building. And then you're going to use your heat pump to take that and bring it to your building. So we're going to be putting in, if we're heating the building, we're having temperatures of -1 to 4 Celsius inside of the pile. If we're cooling the building, we could have temperatures as high as 35 Celsius going into the ground. So that's a pretty big delta T, 30 degrees roughly, 30 to 35 degrees delta T. And that delta T is going to be causing thermal expansion and contraction, as we're going to see. And another option, if we're going to do thermal energy storage, where we're injecting heat into the ground, the temperatures of the fluid could be 60 to 80 degrees Celsius. So that is much higher. You're going to get much larger expansions in that case. And then the ground temperature depends on where you are. It's usually around 10 to 15 Celsius on average in the US. California, we're around 23 in San Diego. I'm sure in Houston, you're also on the warmer side. So you need to make sure that you have an sufficient delta T based on that. So the reason I got interested in this topic is my uncles are plumbers. These are actually my two cousins. I won't say anything positive or negative about them. They're both hard workers. But they install regular geothermal systems. So in regular geothermal systems, or conventional, you drill a borehole, and the same as you would drill for a water well, and you drop one of these U-tube pipes down into the hole. It could be a little bit challenging sometimes depending on the soil layer. And then you backfill the hole with sand bentonite. So these holes that they're drilling for this church here are 300 feet deep. So they have an array of these out in the field, and they're in North Dakota, so there's no constraints on the space. They can put as many of these out there, and they're not going to disturb neighbors or anything like that. But then because they're in North Dakota, it gets very cold and they have a deep frost depth, so they have to trench down 10 feet, bring all these pipes over to a vault, and then bring it to the building. So there's a lot of inefficiencies that are associated with the conventional geothermal systems. And these are very cheap to operate in the long term, but there's a high upfront cost for construction. So how can we reduce that upfront cost? We can put those plastic pipes inside of our foundations. We're already building the foundations, and now we can just add 1% extra cost for the plastic pipes to convert them into energy piles. Energy piles are right under the building itself, so you don't need to have excavation for your frost depth. You don't need to have a long connection for the pipes. These are very popular in Europe. They've been installing them since the late 90s. Austria and UK have a lot of them at the moment. The energy pile movement in the United States is growing. Google, when they built their campus, they put energy piles under there. One of the biggest tricks in the United States is just to make sure that you have good communication between the mechanical engineers who are doing the heat pump and the plumbing and your foundation contractors. And the foundation contractors are the first people going and building stuff out on the site. So you need to have everything planned out where these pipes are going to go, because it's going to be a big muddy mess. And if there's good communication, you can make sure this is successful. We've also been looking at some new types of energy piles recently. We're converting helical anchors into thermal siphons. So we're actually putting carbon dioxide inside of a steel pipe that evaporates and condenses and is another way to transfer heat. And most recently, we've been converting the torpedo piles for offshore floating structures into energy piles. So it's not just drilled shaft foundations under buildings, it's also other areas. And thermal drainage piles, these are porous piles that not only heat the ground, but allow water to be drained through them. So thermal design, I'll just have a couple slides on this. We want to make sure that if we're going to do a conventional geothermal heat system, that the length of this pipe is long enough so that when you apply heat pulses, they're absorbed to the soil by conduction without changing the ambient ground temperature. It's like you pour water into a cup and it just spills over, but it doesn't get hotter or colder because there's such a large mass of ground. And you want to avoid overlap. So you don't want to have any short circuiting of heat that the temperature is going down and then suddenly it's going up without going through your full heat exchange rate. There's some rules of thumb that you can use that 1 thermal ton is corresponding to a certain energy or BTU, and 3 to 4 thermal tons are required for each 100 meters squared of building footprint. And so that means you need 150 meters of heat exchanger per thermal ton. So that would say, well, are you going to design your energy piles to meet the thermal demand? Probably not, because reinforced concrete is very expensive. So we're always going to design our energy piles to meet the structural requirements, and then we get as much heat as we can out of them. So in most configurations of buildings, you can get at least 10 to 20% of the heat transfer for the building. You may say that that's not very good, but if you can cover the base cost of heating and cooling throughout the year, that is a huge savings in cost, because the highest time to heat, if you cut the peaks off of your heating and cooling demands, you really have a big advantage. So you always have to design energy piles for the structures requirements, and then you get as much heat out of them as you can. And then, like I mentioned, there's a conductive heat transfer process, convection of fluid flowing through the pipe, heat exchanger pipe, and then conduction as you go into the surrounding soil. Each of those materials is going to have a different thermal conductivity. So actually the pipe has the lowest thermal conductivity of all the materials of 0.4 watts per meter C. So because this is a complex system, it's very difficult to measure the thermal conductivity of each. So usually we do a thermal response test that will tell us the equivalent thermal conductivity of this entire layered system of the borehole, the concrete, and then the surrounding soil. This just involves heating something up and then doing a line source analysis. And energy piles are shorter, but they have a higher heat transfer rate than boreholes. So just the geometry of the pile has some advantages for energy piles compared to conventional borehole heat exchangers. And then if you're interested, there's many studies on thermal analysis. So going on to thermomechanical design, I think this is the more interesting thing from the geotechnical and structural aspect. I mentioned that heating and cooling lead to these displacements, but then the soil or rock around the pile is going to provide restraint. It's not going to allow it to expand as much as it wants. So if you have a rod just hanging in the air and you heat it, it's going to expand, and there's not going to be any thermal stresses, but it's going to change in length. If you suddenly prevent it from changing in length, either by friction of the soil around it or by having these end restraints, it's not going to be able to expand. So that energy is going to go into stresses. And you need to be careful because sometimes these piles have very high stresses on them due to the weight of the building above. So suddenly you're having this expansion of the pile and you're also loading it. So you need to make sure that you're within the reasonable limits. And you have to make sure that if there are any displacements at the top, you're not having differential displacements that cause architectural damage. So here's just a couple simple expansion diagrams. I use geotechnical sign conventions, so compression is positive, and positive displacements going downwards. That's opposite of structural conventions. So when you heat the pile, you're actually cooling the building. So this is kind of the data I'm going to present here is relevant for Houston, where you're cooling dominated. So the pile is expanding about its null point. It's not necessarily about its center. And you're having restraint due to the building above, the toe at the base, and then side shear on the bottoms. And then when you're cooling it, it's contracting. And depending on the restraint provided, you could potentially have tensile forces being induced in your pile. But it's important to note that these stresses are going to be superimposed onto those due to mechanical loading. So for a very simple case where you have a floating energy pile, this is a pile that has no end bearing. If you apply a load to the top of it, its stresses are going to be distributed somewhat linearly with depth. So at the bottom, there's no stress, and at the top, you're having a stress equivalent to the applied building stress. And then you're going to superimpose on top of that the stresses due to heating. So you add those together and you get an increased stress profile. So you need to make sure that these are within the capacity of the pile itself. And then when you cool it, you're having the opposite case. You could have tensile stresses at the toe. And then another interesting thing is that because you're expanding about the center, the upper half of the pile is unloading and the bottom half of the pile is loading further in shear. So there's some tricky things you have to catch there. And then when you add end bearing onto there, it just changes the shape around a little bit more. So some different options. There's two cases. One is finite element modeling. You need to have a lot of properties, thermomechanical properties of both the soil and concrete. That's for the intact soil. And then you need an interface model to model what's happening right at the soil interface, which is usually disturbed by the pile installation. You need to have some coupled properties and then complex geometry that you usually have to simplify. So I like finite element modeling. I use it in other areas, but it's not always the right tool for every problem. So TZ analysis in this case is a very simple technique. You just need to have a representative stress strain curve for both side shear and end bearing. So we call those TZ and QZ curves. TZ analysis was developed at UT Austin by Lyman Rees and his colleagues, and Mike O'Neill here at Houston developed a lot of the empirical TZ and QZ curves that are used in practice. Talking about both of those analyses, you also need to think about how heat affects soils. Every soil is different, which is why I like geotechnical engineering, because every project you work on is going to be a little bit unique. So if we have those heat transfer processes due to our energy pile, if we have a saturated soil, every soil could be saturated sand, clays. Sands usually have very little temperature effects, unless you're going to very high temperatures. Over-consolidated clays are going to expand and contract this have for like a concrete. So these are very stiff materials. Normally consolidated clays, like the soft clays that you have off the coast of the Gulf of Mexico here, these will actually contract when you heat them. And it's because the water expands more than the solid particles. You have a thermal pressurization, and the pressurized water flows away and you contract. So it's like a negative Poisson's ratio material, but it doesn't have anything to do with the Poisson's ratio. It's just a weird material that when you heat it, it gets smaller. And then unsaturated materials, you also have this thermally induced drying. The water wants to go from high energy to low energy, so it's going to flow away from the heat source. And you have thermal expansion. So we've done some finite element analyses, and there's several studies that I can refer you to in the literature if you're interested in that topic. But load transfer analysis is a much simpler case where we represent the soil as a series of springs attached to the side of the pile, and then have the pile represented as a series of elastic springs, and then another nonlinear spring at the toe. So you need to know the ultimate capacity of each of those springs, and you need to know the stress strain response. And then you use an iterative approach where you ensure compatibility of strains and equilibrium to find the final predicted load settlement curve, mobilized side shear with depth, and then the axial stress strain distributions. So I can refer you to some papers. First, you need to get the axial, the ultimate capacity, both, and it is going to depend on the soil type that you have. And you need to look at both the side shear and end bearing. There's different models for each different soil. And then we need a typical normalized stress strain curve. So these are the O'Neill and Reese and O'Neill curves that were measured in the field for drilled shafts. We've idealized those with just a hyperbolic curve. And it's a hyperbolic curve for loading, but then for unloading, we just use a linear unloading curve. So this is just the normalized curve that is representing this shape here. And the same thing goes for end bearing. We need the unloading because the upper half of the pile is unloading while the lower half of the pile is loading during heating. This is just the iteration process that we use. We have to assume the location, or this is mechanical load analysis. You have a displacement at the bottom of the pile that you impose, and then you iterate until everything is in equilibrium. But for the thermal case, we have a spring at the top and a spring at the bottom. So we need to assume the location of the null point. The null point is the point where there's no displacements. If you heated just a rod resting on the table, it would expand about its middle. But the null point is not necessarily going to be in the middle, because if there's more constraint at the bottom or the top, that location could change. So here's just an example of if you have a spring at the top and a spring at the bottom with no side shear, you could find the location of the null point just based on the stiffnesses of the springs at the top and bottom. So we're going to guess the null point, perform a mechanical TZ analysis, assume that everything expands freely, and then make sure that it's all compatible with the shape of our stress strain curve, and keep calculating until our unbalanced forces go to zero. So with that, you end up with those similar nonlinear curves that represent those cartoons that I showed you earlier. And as you change the temperature, these are going to evolve upwards and downwards. And these are just for 3 different boundary conditions. Going from there. So now I'll kind of quickly go through the 3 different case histories. The first one is a field study. So this is the energy piles installed in sandstone. This is a 1-story building, but we put it on 8 15-meter deep, so that's like 50-foot long energy piles on sandstone. Normally you would just put a slab on grade for this type of a building. So I always like to joke that this is the strongest bathroom in the world. But this is like the shower shave facility that the cadets use when they go for their field emergency readiness laboratory training. They go to the field and do actual construction procedures, and they go back to the classroom and learn about what they did. So this is a little bit of sandy fill at the surface and then silty sandstone for most of the depth. So it's a rectangular building. We have our 8 energy piles here, and 2 of the energy piles we put boreholes so we could measure the ground temperature as a function of distance away from those. And then this is our little mechanical room. So we had to route all of the pipes for this to this manifold area here. Here's a couple of pictures of these energy piles. You always want to put the heat exchangers on the inside of the pile so that you make sure you have adequate cover between the sides of the hole and the rebar. And we always want to try our best to keep the pipes separated, as you can see here, because the cold or hot water is going to be flowing down one side and then coming back colder. You don't want to have a thermal short circuit between the pipes. So you want to keep them farther apart. We pressurize them all with water before we put them in. And then we lift it up in the air. So it's like a long spaghetti without having significant bending. And then we lowered it into the hole. So because this was sandstone, we use the open hole technique. There's some good things and bad things about the open hole technique. It's very difficult in this technique to clean out the material at the bottom of the toe. Whenever you're building a drilled shaft foundation, you want to have a very clean base. So it's going to provide a sound reaction. So you have a strong end bearing. That was not the case for our building here, as I'll show you later. We had actual geothermal water well drillers installing our piles, so they didn't care about end bearing. They just drilled to the right depth and left it there. And I think there were loose cuttings at the base. And I'll show you the effect of that in a second. So this is the dry hole. You can see that it stays open very well through this material. Our strain gauges, we had vibrating wire strain gauges at different depths, and our heating pipes. And then we trimeed the concrete from the bottom up. And then we had to route all of the pipes into our manifold. It's very good that we took this picture here because you can see that the pipes from each of the foundations came in different orders. So we had 1, 2, 3, 5, 6, 7. And this was where we were able to inject the hot water from our heat exchanger. So we have the hot water going into one side of the header, goes down into the pile, comes back up onto the return header. We measure the temperature of the fluids going in, temperature of the fluids going out, the flow rate through each. And from those sets of information, you can get the heat transfer rate. And then we just used a very simple case where we had a bucket of water and one of those tankless hot water heaters that provided a constant heating rate, and heated each of the piles and did a thermal response test. And as I mentioned, we have the vibrating wire strain gauges on each of the piles at different depths. These are tricky because when you heat them, the wire is going to get longer. So it's going to make it look like the pile is going into contraction. Because if the wire is getting longer, it's like looser. So then the vibrating wire strain gauge plucks the wire and it's going to give a lower note because it's going to be a longer wire. So we had to do several thermal corrections on those strain gauges to make sure that they're adequately reflecting the actual expansion of the concrete. Then we had our grade beam at the surface, brought everything together to our electrical room, and built the building. And then while they were building the building, we tracked the change in temperature. You can see that if you're below about 5 to 6 meters, the temperature is relatively constant, equal to the mean annual air temperature. We looked at the temperatures during curing, and we separated those off, and then the mechanical strains due to the building load. So we were able to carry the entire building load in the first 4 meters. It didn't need to be 15 meters deep. So then these are the 3 piles that had a lot of strain gauges on them, so I'll focus on those. Each one of them was a little bit different: a corner pile, an interior pile, and etc. So did a heating response test for each of those, had a constant heat input rate and watched the temperature rise. And during that process, the pile temperature increased, and then we shut it off and it cooled off. So these all, except for this one temperature sensor at the base, the temperature is relatively uniform across the length of the pile, but the strains across the length of the pile were very different. And this is due to the thermal restraint as a function of depth. If we look at each of the strain gauges and look at their temperature versus strain, you can get the mobilized coefficient of thermal expansion, and that gives you a shape like this. We'd expect from an end-bearing pile with friction that the smallest strain would be at the base and that you would have no mobilized coefficient of thermal expansion. you would prevent it from moving. But actually, it was actually pretty high at the base, and that was why we thought that we had loose sand down there. You could just compress that loose sand, and it's able to expand. So our null point was at the location where the mobilized coefficient of thermal expansion was the smallest. If our concrete was reaching the free expansion, which is 12 microstrain per C, then there would be no thermal stress. Here's our temperature profiles, relatively uniform with depth. Thermal axial strain, a little bit higher strains at the top than at the bottom. But because of that pore clean out at the toe, you ended up having the higher strains at the toe. Then we convert those to stress using this equation here. So we measure the thermal strain and then subtract off the free expansion thermal strain and multiply by the Young's modulus, gives you the thermal stress. And you can see that the stress increases with depth up to about 4 to 5 MPa. But then at the toe, because it has pore clean out, the stress was much smaller. So this is the effect of having that loose sand there. So inadvertently, we created ourselves a challenging soil deposit. We could also look at mobilized side shear with depth. We could integrate the strains. If we assume that there was no displacement at the toe, which is not the case, then we could integrate them with depth and get our displacement profiles. The nice thing about this is that we could figure out what the displacement at the top of the foundation would be for our highest change in temperature. And we could check that with respect to criteria for differential displacements. So if one of our piles had expanded by 2 millimeters upwards and all of the other piles were not working, you would have a differential settlement. So the maximum differential settlement we would get is 1/6,000, so it's not going to be a problem. So it's a good thing that we could do this heat exchange and it's not going to cause architectural damage. Trying to simulate it, we want to measure this TZ curve. So the way we did this is we made a special device that we could put down a borehole, expand against the sides of the borehole, and then pull upwards. This is the Iowa State or the handy direct shear test, but we incorporated temperature changes. So we did temperature changes and found that temperature didn't have a major effect on the shape of the stress strain curve, which was good. We could do a simple analysis and use the same normalized stress strain curve at every depth. Then we put that into our load transfer analysis and compared our simulations or our calculations with our measurements. And in general, we got pretty good representations of the thermal axial stress with depth. So this is why it's a very simple tool. All we need is this curve and then an estimate of the ultimate capacity with depth, and we can predict the thermal axial stress profiles. This is just a comparison of the effect of pore cleanout. We looked at the case where we had sand, pure sand at the toe, and the case where we had rock at the toe. So if we had rock at the toe, we would have had profiles like this, but we ended up having profiles like this. So that's how we knew that there was pore cleanout, was through our calculations. Okay, just quickly going on to talk about the two other challenging cases using centrifuge modeling. So I did first some tests at CU Boulder when I was a professor there, and then some other tests on our centrifuge at UC San Diego. We use centrifuge modeling in geotechnical engineering to test small scale models under realistic stress states. So if we have a sand layer and we spin it in the centrifuge, you're going to increase the gravitational forces on that sand layer. So the stresses are going to increase, and you can use some scaling relationships that if you spin something at 50 Gs, for example, it's going to represent a sand layer that is 50 times bigger. So we can do tests in the centrifuge and then extrapolate those to the field. So we can still do the same sorts of tests like we did in the field, where we heat the pile and look at the stress and strain response. But something that we can do in the centrifuge that we can't really do easily in the field is to do load tests. And we can look at the effective temperature on the ultimate capacity of the pile. So we did tests on unsaturated soils and on soft clays. So here's just a summary of some of the tests that we've done since around 2011. So we started with unsaturated soils and focused on dry sands and then on soft clays. So when you do things in the centrifuge, you always get to do some craft projects. You have to make some small scale models of your field structures. So this is our scale model energy pile. This is a floating structure. You can see the cardboard tube and then the lines that are left from the cardboard tube. But we were able to pack a lot of stuff into there. Strain gauges at different depths, thermocouples, reinforcement cage, and then our heat exchange pipes. And then we put this into a tank in the centrifuge, and we could put a lot of instrumentation to measure the temperature profiles around the pile, measure surface settlement, pile settlement, and applied loads. This is just an example of the centrifuge at San Diego. We were focusing on soft clays there. So we consolidated a clay layer into the centrifuge container. We actually pushed the pile into the clay, heated it, and then pulled it back out. And we looked at both long cylindrical piles as well as heated torpedo piles. So most of the tests followed a sequence like this, where we spun it up in the centrifuge, waited for everything to stabilize, applied a seating load, and then heated it, kept the temperature constant. And then for the unsaturated soils, we pushed it downwards to load it towards failure. For the soft clays, we pulled them out. So first we did tests on dry sand, and you can see we did 4 tests there under different temperatures, and the shapes of the load displacement curves are almost exactly the same. So there's no change in capacity of the pile with temperature. We even kind of expected that potentially there was an increase in radial stresses, and then that could lead to some increase in capacity, but that was a very small effect. But when we went on to the unsaturated soils, we saw a big increase in capacity with temperature. We didn't load these all the way out to failure, but we can extrapolate those with hyperbolic models to figure out what the actual capacity was. So we hypothesized that this was due to heating and drying of the soil. And we actually put some sensors into the soil at different locations and found that as the temperature increased, the soil dried out. So we wanted to do some modeling to figure out what the conditions are right at the interface, because you can't put a sensor right at the interface. So we had to come up with some coupled heat transfer and water flow models to look at this thermally induced drying in both liquid phases and gas phases. So we went for COMSOL with this. We had to have a lot of calibration. We did some tank scale tests just to get the parameters to put into this model. And we were able to, this is just the calibration, but then we were able to capture the trends in the experiments from our sensors and the tests. And with that, we could predict what the water content is right at the soil pile interface. And with that, we can do an effective stress analysis. We know what the change in water content is. We can predict what the suction is and get the effective stress. So with this, we know how the effective stress is changing with the drying of the soil as due to increases in temperature. And we can then put that into effective stress analysis here to see how the side shear capacity is changing due to the drying of the soil. And our predictions with either alpha or beta methods were almost spot on with the experiments. So just the final example here. This is where we wanted to test the effective temperature on the pullout of piles in soft clay. We did one that has an end-bearing pile and these torpedo piles. So the way that you would do this, if you're like in the Gulf of Mexico, a torpedo pile, you would drop this off the side of a ship. It would embed itself below the seabed surface. And then you would have an electrical cable connected to it, and you would heat the pile up. So you're not necessarily trying to harvest energy in this case, but you're trying to use the heat to improve the ground. So the heat transfer goes away from the pile, and that's going to drive water away from the pile and cause consolidation. So that's kind of what's shown here. You increase the temperature of the pile, maintain it. The water pressure increases, and then when you increase the water pressure, that creates a gradient. So as the gradient dissipates, it goes down to zero, you end up having a consolidation process. So we call this thermal consolidation, and that leads to an increase in undrained shear strength. So I have a lot of other experimental data that I could show you here, but these are just the final results showing that as you increase the temperature, the pullout capacity increases. And in fact, the pullout capacity can be as much as 100% if you heat the pile up to 60 Celsius. So I think this is a good potential area where we can use heat to improve the capacity of our piles. Okay, so I went through a lot of topics there very quickly, but I hope I showed from the case history in the field that energy piles are an established approach where we can decrease the installation costs for heat exchange systems and where we're not going to have major problems. Thermal stresses are going to be within acceptable limits. They're going to be lower than the compressive strength of concrete. We're not going to have major thermal differential deformations. So I think that those things are all good signs that energy piles will work for standard projects. But we should always be careful to understand the effects of heat exchange on the soil. Are we going to have a change in heat transfer? Are we going to have changes in capacity? And if we want to predict those, we need to have good numerical simulations to interpret some of the things that happen in the field. You need to interpret what is the effect of this pore cleanout? What is the effect of temperature on unsaturated soils? What is the effect on thermal consolidation? So I think there's still a lot of opportunities in the future for new numerical simulations that can be developed. And we're still continuing to work on this topic, even though it's been going for a while. So with that, I'd like to thank all the students that have worked with me on this project over the years and several different collaborators. So with that, thank you and happy to take some time for questions.
Any questions?
Thanks for your talk. I enjoyed a lot of new things from you. I was just curious, in the case, towards the end of which, in the case where you can use the temperature to increase the capacity of these piles, what are kind of the scenarios where you can actually take advantage of something like that? Because, for regular structures, then if you're going to take advantage of that, then you have to make sure that the temperature is actually higher all the time.
Yeah. So you definitely. So the main application for this are for floating offshore structures for wind turbines or petroleum. So I first started to work on this because we were working with Petrobras. They're the main users of torpedo piles. The problem that they have there is that they need to increase the capacity of their anchorage system to support some of the floating structures that they have. And the only way that they could do it was to install more piles. It's very, very deep water depths. So you can't do any, and it's clay. So you can't do chemical treatment. You can't do vacuum surcharge, some of the things that we could do onshore. So really there's no other way to get more capacity besides putting more piles or longer piles or heavier piles. So this is a way that potentially you can get an increase in capacity for those, regular size piles. Because the ships that they use to install those have to have a huge crane that can handle them.
So all your test time concrete piles, right?
Yep, regular.
Concrete
except for these torpedo piles.
Yeah, concrete is a thermal insulator, right? How's
Yeah.
the heat flowing? Have you tested steel piles instead of concrete piles to produce more energy?
Yeah. So as I was mentioning at the beginning, the conventional approach is to use the drill shaft foundations, mainly due to the geometry. So there's some big advantages for having a large diameter, short pile for heat exchange, but it's a So, and one thing about these heat exchangers is that they're never very fast. So you can never get the heat right away. They're always a slow heat up and cool down. But for example, this schematic here is not really to scale. This would be a steel pipe with the helices on it, and the top and bottom are closed. If you pressurize that with, well, for one thing, you could just put a heat exchange loop inside of that, and then grout it into place, and then you have this steel pile. But we were looking at putting compressed CO2 inside of it. So CO2, when you heat it, it evaporates and then condenses, and you get a convective cycle, as you can kind of see in this picture. So that's where we're using steel. And then if you're doing the torpedo piles, that would also have to be steel. But then the heat source in that case, you probably wouldn't put a geothermal loop. You'd have a thermoelectric element inside.
So when you transfer heat in the reinforced concrete, will it corrode the steel faster because your pipes are touching the steel first, right?
But it's a plastic.
Yeah, but heat won't be transferred to the steel.
Yeah, I mean the steel will reach the average temperature of the concrete. So increase in temperature probably will lead to more corrosion.
Durability is not a problem.
Nobody's ever excavated one of these and tested it. It depends on what your groundwater conditions are or soil conditions are. That's one of the reasons that we want to make sure that you at least have a good concrete cover between the soil and the steel. If your steel was touching your soil, you definitely get a lot more corrosion.
So this is like some kind of convection analysis that is done to control the rates and the water flow.
So you want to make sure you have turbulent conditions of water flowing through the pipes. When it's turbulent, you're having good mixing. If it's laminar, then you have no flow at the boundaries. So you have a hot plug of water going through. But if it's turbulent, there's basically some coefficients that you can do a boundary condition. And then you have convection into the solid materials. In ComSol and places like that, they have a pipe flow model.
Yes.
Sure.
Okay, for your presentation. So my question might be trivial, but I was wondering how maintenance of this systems comes here to balance, because as it's much harder to keep the whole pile there through just 50 feet. Because you use pressurized water, right? And pressurized fluids. Assume the pipes need to be maintained.
So plastic has been used in landfills in very harsh environments for very long periods of time, and then the HDPE is very resilient. So as long as it's okay when it goes into the concrete, it's probably going to be safe. So you wouldn't ever necessarily need to maintain that element within the pile. The ones that I have in Colorado, I built in 2010, and everything is still flowing okay. 14 years. The main maintenance is with the heat pump unit, the ground surface. You just need to make sure that everything is safe.
In your study for the finite element simulation, your pile and soil, how did you simulate the interface?
Yeah, that's the tricky part. For that particular simulation with my collaborator, Rich Ruggiero, they had a rigid connection at that point. So they didn't even have the slip connection. So it wasn't a very good simulation of energy clouds. They've done more modern simulations. You have to have some sort of a reduction factor to go from the soil stress strain response to the soil pile stress strain response. That's one of the reasons we liked to use those measured curves. Measured curves like this, that we measured the concrete soil interface stress strain curve.
I had a related question. These are like, they are assuming these are mostly static.
Yes. Dynamic.
Schematic.
Yeah, I mean, the displacements are very small. Yeah. You're probably still going to be in this elastic region unless you're having, if you're using it for heat storage, potentially you could start to pass. And especially if you're in the soft clays, your site shear capacity is not very high. So smaller changes in temperature could lead to thermal failure at the end of this.
Just wondering, you're expert in this field, if the effects of this thermal condition, changing thermal conditions of dynamic stress have been studied in detail.
You mean the wave velocity that we?
Yeah.
No, I don't think anybody studied that.
And it could become important for deep.
Yep.
Okay, anyone else? Okay, let's thanks for speaking.
Thank you.